I know that it's the privilege of the last speaker to thank the organizers, but I'd like to thank the organizers for organizing this and inviting me. So, OK, so what am I going to talk about? Well, I'm not changing it too much, but my title was Can Local Picard Group and Gross-Hopkins Duality. And then I looked, and I realized I had 45 minutes, so I decided to shrink the title. So I'm going to talk about Can Local Picard Groups. But I'm going to take out the Gross-Hopkins duality part, and I'm going to stick the word exotic in front. OK? So at the end of the talk, you'll understand why that shrinks the topic. OK, and the stuff I'm going to talk about, well, the stuff that's new-ish is joint with Irina Bobkova, Paul Gers, or Gors, I guess we've been taught, and Hans-Werner Henn. OK? OK, great. So, so first, let's just sort of ease into it. So if you have C with a product, which I'm going to denote by a tensor, and I, the unit object, a symmetric monoidal category, then the Picard group of C is going to be the group of invertible objects. So the object X such that there's some Y and an isomorphism between X tensor Y and the unit. Okay? And in fact, I look at this modulo isomorphisms, and provided that this is a set, it's a group, and that's called the Picard group of the category C. Okay? So for this talk, the kinds of examples that I'll have in mind come from homotopy theory. Ooh, surprise. OK. So if R is a ring spectrum, there's going to be sort of two classes of examples that are going to come up in what I'm going to say. So first, I could look at, and I mean homotopy categories. So the homotopy category of R module spectra. OK? Well, in this case, the monoidal product will be tensor over the ring spectrum R, and the unit will just be R itself. OK? And in this case, I'll write pic R for pic C. And this example will come back. OK? Now, this Picard group, I mean, it always contains some cyclic group generated by the suspension spectrum of R. Okay? The cyclic group may not be Z. It may be torsion. It may be Z mod something if R is periodic. Okay? But it always contains a cyclic part. Okay? So now I want to give some examples. So the one that we always start with is, well, if R, so this is going to be R here. If R is just the sphere spectrum, then this is just the Picard group of the homotopy category of spectra, and it's just the integer. So it's generated by the suspension of the so S1. Okay, so it's just a cyclic thing. So there's a lot of examples, but I picked a couple. Okay, so I'm going to jump to if the thing we're looking at is KO. Well, the Picard group then is a copy of Z mod 8 generated by the suspension of KO, and you should see the 8 as coming from Bott periodicity and the fact that this spectrum is periodic. But they're not always cyclic, so if you take the spectrum T and F, and the capitals are, the order of capital letters and small letters is important here, this is going to be a Z plus a Z mod 24. So there's a cyclic part, but then there's something else. Okay? And this is, I don't know. This is, I think this is going to be the first credit I'm going to give. So I'm going to put Matthew Stoyanovska here. And maybe I'll write that as MS later on. OK? And the other ones, I don't know. This seems like classic stuff. perhaps even an exercise. OK, so this is the first. So Picard groups of R module spectra is going to be one of the examples that's going to come up in my talk. OK? So in the same sort of spirit, the other kind of example that I want to be thinking of, I'm going to take C to be the homotopy category of R local spectra. OK? And now the monodal parabolic is you smash, but this may take you out of the category of R local spectra, so you relocalize. Okay? And then the unit object is going to be the sphere localized at the spectrum R. Okay? And so here, in this case, I'll write pic sub R for the Picard group of this category. And I want to look at some of the examples. Okay? So again, this always contains a cyclic group on the unit, but it may contain other things. Okay? So for example, well, so let's start with one that doesn't. So if R is H, maybe HZ or HZ localized P or whatever, then you just get a copy of the integers. Okay? So there's nothing more interesting than just the suspensions of the unit. Okay? But let's see. Let's skip to, suppose that I take P completed K theory at the prime 2. Then I get a copy of Z, but then there's, again, another invertible element, which is different and is interesting. Perhaps one might say exotic. Okay? And then if you take, say, let's do mod pk theory, and what I'm going to write is for an odd prime, then you get a lot of stuff. So there's a cyclic thing, but I'm going to put it inside something else. There's actually a copy of the p-adic integers, and then there's other stuff. There's also a torsion piece. OK? So as you can see, these answers, I mean, there's a lot of different things that can happen. OK? And in fact, so on this list in a second, these are all examples. Like the left column is a bunch of examples of this kind. And this is where we're going today. OK? So let me make some definitions. So OK, so this is a talk on chromatic homotopy theory. So let's go chromatic. So chromatic homotopy theory is looking at these kinds of examples and sort of generalizing at higher heights. OK? So let me just put some words on the board. So, and of course, there's some credits to be given, but it's all on this board first. So I'm going to leave it at that. All right, so now let's fix P and an integer n bigger or equal to 0. Well, by E or En, I mean Morava E theory, which is a higher form of P completed K theory. Okay? So E1, by higher, I mean that E1 is P completed K theory. So Kn is a higher version of mod pk theory, and so K1 is just KFP. Okay? You can choose it that way. Now by G or Gn, so this guy has not made an appearance yet on the board, but it's a higher version of the Adams operation. Operations. Okay? So what's G1 then? Well, the Adams operation are just a copy of the units in the p-adic integers. And just like the Adams operation act on P completed K theory, there's an action of this group on the spectrum. Okay? I think there's a lot of people in the room that are responsible for this picture. Okay, so thanks, guys. It's great. OK, so these are the kinds of the categories that I'm interested in this talk. So this is, people call this Hopkins Picard group. And it's, so I'm going to write pic sub n for the Picard group of kn local spectra. So my prime is fixed, and I look at the Picard group in this sense for the kn local category of spectra where I'm looking at where I localize with respect to these higher versions of Monte K theory, okay? I mean, these are interesting. Like, what's the biggest answer I wrote on the board? Well, big sometimes is hard to measure, but I mean, this is uncountable, so this wins, okay? So this is, I mean, these Picard groups are very rich, okay? And at this point, I can, now the notation matches on this table. You see pic n is written on the left-hand side for some values of n and p, okay? And as you see, the list is not very long. There's a lot of things we don't know. But that's the topic of the talk for today. And I'd like to say, I mean, there's a lot of I mean, if you look at the list of names, you realize there's probably a lot of hard work that goes into producing such values, okay? So that's the Picard group. There's a lot of things I could say about the Picard group. And I'm not going to say them all. So I've picked a path through the woods. So if you know the woods, you'll notice, but what about the waterfall over there? OK, I might not go and do all the hits, but let's see. The first thing I want to say is, OK, so this is maybe a bit of it's going to be a bit of an aside for a second. So I want to look at En here. So suppose I have a spectrum X, and I write En star of X is going to mean not quite the En homology of X, which is what it should mean, but you take En, you smash with X, and then you relocalize, okay? This process may not give you back this thing. It will sometimes, but not always, okay? So if you look at this, well, okay, so I said that, well, first, this is an E star, so now I'm dropping the N. This is an E star module, okay? So it has an action of the homotopy groups of Morava E theory, but it also has an action of the group G coming from the action of G on this factor, okay? So it's a twisted G En star module, okay? So you could look at the category of such things. So it's just an algebraic category. So G E star module, and look at its Picard group. And that thing is usually called the algebraic Picard group, okay? And so this is a definition. It's not known if everything in there is of this form, but there definitely is a map from pic n to the algebraic Picard group, okay? Which maybe I'll write epsilon n. Okay? And it just does this process. It takes X to En star of X, okay? So why is this thing interesting? Well, in some ways, this is, so you can use this as an approximation for pic n, which is the thing that you're interested in computing, okay? But OK, so if you're approximated within, then there's obvious questions to ask. So the first question is epsilon n surjective? Okay? So this is an open question. We know that it's surjective in some cases, and there's others that we don't. Okay? But in general, it's an open question. And then it could also have a kernel. So I'm going to write, so this is going to be my definition for the symbols kappa n, which is the kernel of this approximation to an algebraic gadget. Okay? And let me just like drive it in. Okay? So these are the x's such that if I go there, I'm in the kernel. So what's the unit in here? The unit in this thing is E star with the action of G. Okay? So these are the x's such that their E star homology in this sense is the same as E star, which is the E-star homology for the sphere, together with all of the action of the higher atoms operation. Okay? So these are the things, these are the things that X that look like SKN to algebra. Okay? So these things, algebra thinks they're spheres. Okay? Okay, so then the other question is kappa n 0? Okay. So for today, I could go two ways. I could spend a long time talking about the algebraic Picard group, but that's not what I'm going to do. I'm going to focus on kappa n. So maybe I will say one thing about this guy, though. So let's see. I want, maybe if I use a different color. So this thing, is roughly computed. There's a small technicality here, but it's not, it's trivial. It's computed by some group cohomology. So it's computed by, you take h1 of g with coefficients in E, the unit, in pi 0 of E. Okay? So roughly, this thing knows everything about the algebraic Picard group. So since this is so easy to compute, we don't focus on that part. Okay? So that's just like the token joke, right? Okay, so at least we have a name for it. Okay? Okay, so computations for this group you can see in this board. So this would be the algebraic Picard group. Okay, so that's the kind of answers it spits out. And I think the newest one is the last line, which is due to computations of Hans Werner Henn, and I'm told that we're supposed to take them with a grain of salt, right? That's but there's a lot of hard work that go into that. Okay. Okay, so let's see. Now let's look. So now I'm going to shift my focus back to this thing here. So this thing, OK, so now I can give a, so this thing is called the exotic Picard group. OK? So that's the exotic in my title. So now I'm going to shift focus to kappa n. Okay? So some example, if you look at kappa 1, well, kappa 1 is, so it's going to be 0 if p is odd, and it's going to be a z mod 2 if p is equal to 2. And this z mod 2, I didn't put it in here, but this z mod 2 is related to that z mod 2. Okay? So this piece here for KFP, so level 1 is in this picture. So this is mod p. This is the algebraic Picard group at level 1, just like on that table. This is related to that Picard group, and this is the instance of that z mod 2. Okay? So if we look at kappa 2, that's 0 if p is greater or equal to 5, and I think that's due to Hopkins, Mahold, Waldowski, which from now on will be HMS. And if p is equal to 3, it's a z mod 3 times a z mod 3. And if p is equal to 2, it has order 2 to the 9th. And it's one of two groups. And I picked the one I think it probably is and put it on there. But it's in red surrounded by question marks. So, all right. So it looks something like that. It's close to that. And so this is Gers, Henn, Mahold, Resk, which will now be GHMR. And this is us. Okay. All right. So for the rest of the talk, and now I am great. OK. So for the rest of the talk, I'm going to talk about detecting. You can go. OK, so for the rest of the talk, I'm going to talk about detecting elements in these exotic Picard groups. Okay? So the next section that I'm going to also detection of elements of kappa n. OK, so we're algebraic topologists. We want to detect stuff. We want to compute something. What do? We filter it. And if the first filtration is not enough, we put a second filtration on or something. And then we put as many filtrations as we need to figure out what the answer is. Okay? So the first filtration, and this has been along for, or like these kinds of methods, these ideas have been around for a long time. And some people have thought a lot about them, like Shimomura, I know, has thought a lot about this stuff. So first, to give it a recall that if I want to look at the Can local sphere, which is the unit of pic n, right? So that's equivalent to the homotopy fixed points of E with respect to the group Gn. And this is Devenot's Hopkins. And it was also worked on a lot and sort of made even more precise by one of the organizers, Davis, okay, in his thesis. So, OK, so we have this equivalence. And there's a fixed point spectral sequence, G. So actually, so now coming from this filtration, so now if X is in our group, kappa n, there's a spectral sequence, which looks like E star of X and converges to the homotopy groups of X. Okay? Now, X is in kappa n. Okay? And I said, if you're going to be in kappa n, that means that algebra doesn't know that you're not a sphere. Okay? So this is an algebraic gadget, right? Group cohomology and these coefficients. So if X is in kappa n, this thing looks exactly. So the E2 term of this spectral sequence, this is a T, looks like the E2 term for the sphere. Looks like the E2 term for the sphere. Okay? So now this one goes to pi T minus S of S K2. And OK, so now suppose that X, so if X is not the sphere, so if you're trying to catch something good, well, then it better not be the case that there's an element here. So if X is not SKN, there's a 1 in here, in H00. This gadget, that's a ring, OK? So there's a 1 in the group cohomology. And that thing, if it survives the spectral sequence, it's going to give you a map from S naught to X. And just because of everything that's going on, because of this thing is in the Picard group, that map will give you a Can local equivalence, OK? So if 1 makes it, then X is the sphere. So if X is not the sphere, then 1, so then these things can't be, so these things can't be equal, and 1 must support a differential in the spectral sequence for X. Okay? So we can let kappa n, say R, be the X in the Picard group in the exotic part, such that, say, dlx, so the differential in the spectral sequence for X, is 0 for L less than or equal to R. OK? So you filter it by how long this unit survives through the spectral sequence. Okay? So I mean, the filtration goes like you have kappa n. So the first thing that can happen is, because of sparseness, the first thing that can happen is a D3. So you get kappa n3, kappa n5, ... OK? So you get a filtration like that of the Can local Picard group. OK? And so another question that's open is, what kinds of elements in, say, I'm going to write it as star, and I'm going to put my star here, can be targets. Okay? So there's a list of elements which are in the right bi-degree to receive a differential from 1, and a question which I don't think we know the answer to is how do you decide which in this list are, are allowed as targets? It's definitely not all. At the prime 2, there's some stuff that just doesn't really get realized. It's just kind of noise. But this is a question that I think Shimomura has thought about a lot. Okay? All right. So you get one filtration that way, and that's sort of one of the classic ways to think about this Picard group. So the second the second filtration is the one I'm going to spend more time on, but I wanted to tell you about this one because it sort of helps you warm up thinking about what's going on with these guys in the exotic Picard group, okay? So differentials on the unit, that's something that happens to them, okay? And that's how you might detect them. Okay, so the second filtration, so now let's take G, a subgroup of the Morava stabilizer group, and I'm going to make a definition. I'll actually take the group with me. So let's kappa EHG be the elements of kappa n such that if you look at E star of x, sorry, it's not kappa n. Okay. The elements of pic EHG. So by that, I mean the Picard group of EHG module as what I erased here. That was the motivation for talking about this kind of example. And we look at those such that if you look at E star of x, that's the same as E star EHG as an G E star module. Okay? So both these things are in this algebraic category of twisted G E star modules. And I'm looking at those x such that the algebra doesn't know the difference between x and this guy. Okay? This guy is the unit in this category. Okay? So where kappa, it's like the exotic Picard group of the category of EHG modules. Okay? Now, there's a map. So if I take kappa n, I can map it to kappa n, kappa EHG by taking a guy and smash it with EHG. Okay? So maybe let's call this epsilon g. So this gives you another approximation, different than this algebraic approximation. Okay? So now, of course, this map could have a kernel. Okay, and I'm really sorry. I'm going to call it kappa upper G. I also thought about calling it kappa with taking a color and scratching the G off because it takes me forever to remember, like, does it know about it or does it not? Okay, so this is the stuff that doesn't know about, that EHG does not seize. Okay, so that's the stuff that when you smash with EHG, you get EHG back. Okay, so these are the x such that x smash EHG is EHG, okay? All right. And then you can ask all the good questions. So is epsilon g, so for a fixed g, is this surjective? Is kappa ng 0? Okay, so how good an approximation is this? And the answer varies on the height, the prime, and the group you choose, okay? So let's see. I want to put a filtration on things, so I'm going to pick some groups. I'm going to pick a nested sequence of groups, and it's going to give, using this, these guys are going to filter this guy, okay? So I need to tell you which groups. So the first one is I'm going to let f in G be a maximal finite subgroup. F is for finite, which contains all the p torsion, okay? So this group varies depending on the prime and the height, but that's what I'm calling it. And the other group is I'm going to call G sub 1. And this guy is the kernel of a certain map. So the group G emits a map to the p-adics, with people, the units in the p-adics, which people call the determinant. The units in the p-adics have torsion, so you mod out by that. And then you get, so this map here is surjective, and this group is isomorphic to ZP. And G1 is just the kernel of that map, okay? So that's the definition of G1, okay? So G1 is a big, a big closed normal subgroup of this thing. Its quotient is a copy of the p-adics. So it's kind of like almost everything, okay? You've sort of stripped out one of the sort of cohomological dimension and kept everything else, okay? Now G contains G1, and that actually contains the torsion, okay? So you get a filtration. So the kappa n contains kappa nf, or stuff that doesn't see that, kappa n G1, stuff that doesn't see that, okay? So that's a different filtration. It's very small. Probably if one were to try to do this at higher heights, it might be useful to use more groups. I don't know, okay? But this works for the heights we're looking at, which is n is equal to 2, okay? Okay. So let's see, for example, if n is equal to 1 and p is equal to 2, then if you look at EHF for this group, the maximal finite subgroup is just the plus or minus 1. So you're going to get EHF is just 2 completed K-theory. Okay? And then you're looking at a map from kappa 1 to the Picard group of KO modules. And so this is the exotic part. We saw at the beginning the whole Picard group was Z mod 8, but the part that's not seen by algebra is a Z mod 2 generated by the fourth suspension of KO, it turns out. Okay? And so this turns out to be an isomorphism. Okay? So there's a guy out there such that this is EF, such that if you smash with it, there's a guy in the Picard group such that if you smash with it, you get sigma 4 KO. Okay? And there's no kernel. That's a height 1 phenomenon. Now let's look at n is equal to 1. For both primes, so for p is equal to 2 and 3, if you look at EHF, that's just TMF K2 localized. Hmm? Thank you. Okay? So TMF is like the height 2 version of KO. Okay? So that's what you're picking up. So the question is like, what element of the Picard group, if you take an element of the Picard group and smash it with TMF, do you detect it or do you not see it? Okay? Okay. So let's see. Let's do the prime 3. Okay. So I have to erase my boards. Oh, thank you. I should use that. So if p is equal to 3, this is so this thing is HMS, and this is GHMR. You get, okay, so you look at kappa 2, you map it to, let me just skip the middle thing. You map it to kappa of EHF, which is the Picard group of K2 local TMF modules. And this thing, it turns out, is a Z mod 3 on sigma 24 of TMF. I should write TMF on both, but you're going to survive. Big. Okay. So I just write it this way. Sigma 24 EHF. Okay? And it turns out that this map is surjective, but kappa 2f is not 0. It's a Z mod 3. Okay? So this thing is a copy of Z mod 3 times Z mod 3 as promised. But EHF does not detect all of kappa 2. Okay? So it's not good enough. And then at p is equal to 2, this is BBGH. Again, you're not going to be able to see everything with TMF. So you take kappa 2, map it to kappa of EHF. And this time, this is a Z mod 8 generated by the suspension of EHF, the 24th suspension of EHF. I think these kinds of things, I know you can find in MS, but you'll have to ask the organizers to know. Is it you guys? Did you guys prove that, or is that? Don't know. Folklore written up, finally, by Stoyanovska Matthew. OK, so this map is surjective, and the kernel kappa 2f, this thing fits in an exact sequence, it turns out. So this thing, let me just put, has order 2 to the 6. OK? All right. So let's see. 907.
Who is the second B in
BGH? Bobkova.
No.
Irina Bobkova, yeah.
What is NS?
Matthew Stoyanovska. Yeah. I said these things. I'm just joking. Keep asking. OK, so at this point, I'm going to say just one sentence. So these maps here, they're not only surjective, they're split. And so this is, I mean, at the prime 3, they have a lot of control over the situation. At the prime 2, I mean, the part that was supposed to be about Gross-Hopkins duality is that to get that this map is surjective, so the strategy for surjectivity is you look at the Gross-Hopkins dual of the sphere. This thing might have a twist might be twisted by an element of the Picard group. And that thing that's twisting it, maps to a generator here, OK? And the splitting you get from this other, the first filtration. Remember, we have 2 filtration, we can play them off each other. So it turns out that what you're seeing goes into different pieces of the filtration, and you can sort of get that splitting that way. And the same method works at the prime 3 too, although I just don't think that's how they did it, OK? They just construct the thing. But you can ask, they're all here. Well, not all, but OK, so in spirit, for sure. OK, so OK, so let me see. So I'm behind my schedule. I had like some time. 45 minutes is not a time I'm used to planning for. But let's see, what of this guy? That's what I want to talk about next. Okay. All right, so in general, if I have, how am I going to put it? So kappa n G1, which is then supposed to get, so the stuff that's not seen by this group, in general, you can identify with the following group. So you take En Gn1, so this is the same group. So the homotopy fixed point with respect to that group, you take pi0 of it, you look at the units, and then you take those whose Adams-Novikov's filtration is bigger than 0. OK? And then if you have an element in here, so this is the same sort of, you see this trick. So this trick seemed to have been born in this Hopkins-Mahold-Sadovsky paper. They construct a bunch of elements of the Picard group in there. And this is just like a play on that strategy. So you look at EHG1. Usually there's a familiar fiber sequence where you take a topological generator, so of G modulo G1, which is a copy of the p-adics, okay? And then if you put C minus 1, you can construct the KN local sphere this way, okay? So what's the trick? Take a lambda in here. Blue is probably bad. So take a lambda in here. Change 1 to lambda. And then the fiber is probably going to be different. And this fiber is going to be in this group. OK? So you just twist the fiber sequence. Okay? So from this theorem, from this result, you see that, OK, so the theorem of GHMR is that kappa 2 G1, and then this is the stuff that's not seen, is Z mod 3. And it just comes from knowing what's in this group, OK? And BBGH, kappa 2 of G1, and so this is P is equal to 3, P is equal to 2. That's a Z mod 4 plus a Z mod 8. And again, it's just coming from a computation of this group. OK? All right? So now, the extra piece of the theorem for GHMR is that this is actually also kappa 2F. OK? So at the prime 3, this step in the filtration is trivial. These two things, these two filtered pieces are equal. OK? So you compute just like there's only one step to break things down with. OK? At the prime 2, this is not the case. So at the prime 2, if you want to see what's the quotient in this piece of the filtration, you're going to get a Z mod 2. OK? All right. So there's something, an extra level of complication at the prime 2. What a surprise. OK? But I want to spend the last 5, 6 minutes, or no, I have a minute. OK, well, OK, the last 4 minutes, since you guys have no questions, OK, to talk about the strategy. OK, so let's see. There's a certain subgroup G which hasn't appeared yet. Now where P is equal to 2 is equal to N. OK? And if you do EHH, you get TMF with level structures K2 localized. OK? So that gives you a spectral sequence, which is called the topological duality spectral sequence. OK? And it looks like this. E1 ST of X, so the E1 page is pi t of TMF smash X. If S is equal to 0, pi t of TMF 0, 3 X. If S is equal to 1 or 2, and pi t of sigma 48 of TMF smash X if S is equal to 3. And this converges to pi t minus S of E, H, G, 1 smash X. So in my notes, there's a red thing that says lie warning. See Hans Werner's talk for a correction, OK? I'm oversimplifying things. There's an extra layer of complication. But, you know, so lie warning. But if you go to Hans Werner's talk, you'll understand. OK? OK, so there's the spectral sequence. And you know, this is how we compute pi. If you plug in the sphere for X, this is how we compute this thing. So the last thing I want to do is show you a picture of that thing. OK? I never go there. That's why I really wanted to go here. OK, so here's the duality spectral sequence. So I've drawn it, you know, T minus S grading. So if you want a homotopy group, you look in a column. So in the rows, you have the homotopy groups of TMF. So squares are Z's or fat Z's, because TMF has a lot of stuff in it. Dots are Z mod 2s. Dots circled are Z mod 8s. You know, the usual thing. OK? Differentials go in the direction that I've drawn them. Computing the D1 is a lot of work, but you do it. And then you get the E2 term, which is on the right. So it's a lot of stuff. Like these white boxes, you should think of as it's like this annoying stuff that's in the way, and it actually just all like cleans up, okay? And then if you look in the red column, that's pi0 of EHG21. And you get a Z, which is the stuff that has not Adams-Novikov's filtration. So there's this piece here. So the Z does not satisfy this condition, but everything above does. And you have a Z mod 8 coming from the top TMF and an assembled Z mod 4. Okay? And then this other piece here. So remember I said exotic things means differentials on a unit. Okay? So I don't have time to get into it, but stuff that would be in this in-between here would be things that, these are things that such that you smash with EHG21, you don't get EHG21 back. So this spectral sequence should not be computing the homotopy groups of EHG21 for an exotic guy. Okay? And one of these exotic guys, it turns out, has the same E2 term. Okay? So what do you need to see? You need to see a differential on the unit. And the only thing you can get is a D2. And the obstruction group is Z mod 2. And that's where the Z mod 2 is coming from. Oh, you have 3 minutes for questions. Okay. So the answer is no. Like the exotic thing, it's believed to be a finite P. Well, I think it's known to be a P group and believed to be finite. But we don't have proof of this. It's tied to knowing that the homotopy groups of the KN local sphere are finitely generated ZP modules, where ZP is the p-adic. So this is something we don't know. Like so no, we don't. Yeah.
You don't know these are finitely generated?
No. Yeah. So at least not that I don't know. Yeah. And yeah. So. But I mean, they're believed to be they're believed to be finite P groups. So like it's just there's this technical thing about something being finitely generated in general that people sort of seems to get away from people. Okay.
Is there a conjecture about the rank of the algebraic Picard?
Not that I know of, but that's more like that one. It's more like on me. I haven't heard of one. Sure, I don't know. Hans Werner, do you know if there's a conjecture for the rank of the algebraic Picard group? Yeah. Mike? Huh? Rank 2 always. Okay. For n bigger or equal to 2? See, that's why you can't trust patterns.
Anyone else? I'm going to ask you a question. So how many of these elements do you, for n equals 2, p equals 2, can you realize in
like construct?
Yeah.
So we can construct this. We can construct this.
By resolution?
But using this thing, yeah. And then we can't quite construct this guy. I mean, that's part of not knowing the full answer yet. But well, actually, I don't know. So this one, I guess we can construct it, but it's more indirect. So we can construct EHG21, an EHG21 module that's going to have that spectral sequence. Just you tweak the construction of that spectral sequence to make that differential happen. You write a tower of vibration, okay? And then I think you can sort of convince yourself that. Well, and then the next step is murky. So I'm not gonna let me just hold back on that. But we have begun its construction, but it's not clear how to terminate it. Yeah.